Well, good evening, everybody. My name is Bert Dicht. I am the Managing Director of Membership for the National Space Society. Thank you for joining this meeting of the HAL 5 NSS chapter. We're doing doing things a little bit different here because we have people in a live location in the library, and we also have people online. So it's a little bit different. I'm just going to start off and do a quick introduction and then turn it over to our live presentation, and we'll go from there and hope all the technology works. So it's my pleasure again to welcome you on behalf of the National Space Society, what we consider the premier space advocacy organization. We're dedicated to space exploration, we're dedicated to space settlement and space development. We do a lot of different activities, and the slide you're seeing right now is what's called our International Space Development Conference. This is the ISDC. This is our big annual Space Development Conference. It's actually the 42nd conference that's coming up in May in Los Angeles, Memorial Day weekend at the Sheraton Gateway. The theme for ISDC 2024 is No Limits. We typically get anywhere from 1,000 to 1,500 people, including about 500 students come for a space development contest. So we're looking forward to a really great event. You can see some of the great sessions that we have planned, everything from space solar power to space law to living in space to Mars. We have several astronauts coming as well. Susan Kilrain, who was a space shuttle pilot, former F-14 pilot as well, and Jose Hernandez, who you might have seen the great Amazon Prime session on him, 1,000,000 miles to the stars, and about his experiences applying to the space program. About 10 different times he applied to the astronaut program, wrote a great book, and again, they made a great movie about his life. So he will be there. We have Dr. Alan Stern coming as well from New Horizons. So it's going to be a really great session. We invite you to join us there. Registration is now open. There is actually right now a early bird registration that you can get through the 18th of April. So we hope to see you there in Los Angeles. Just go to ISDC 2024 if you go into Google, and you can easily get to our website for that. But it's isdc.nss.org. One of the other big things we do within NSS is our Ad Astra magazine. This is one of our premier space development magazine. We publish it 4 times a year. Great authors, great photography and artwork. The editor-in-chief is Rod Pyle, the renowned space author, and it is an amazing magazine. So the first issue is just published this year, what we call 2024-1. Some great articles, for example, unveiling the mysteries of a metal asteroid. That's the Psyche mission to that metal asteroid. Space for all of us, on to Alpha Centauri. Everyone's gone to the moon, and much, much more. It's a great, great magazine. So if you are a member, you probably have received it now, and it's also posted online in our membership portal. So hopefully that'll encourage some individuals to maybe think about NSS membership. If you're not a member, just ask one of the individuals there, and if you're actually in the audience. But I can also put some of the information into the chat for those that are online as well. One of the other big things we do, as I said, we're a space advocacy organization. We just finished up what was called the March Storm. This is a premier space development advocacy event in Washington, D.C. And people come from all over the country. They get trained, and then they go out and visit the offices of members of Congress, the Senate, and so on. We had 27 citizen advocates met at this last one in March. They visited 75 different offices, including the Office of Space Commerce, and very successful. Their big objective this year was focused on an act called the Commercial Space Act, and this has 3 components: extending the learning period on commercial human spaceflight, designating the Department of Commerce as the federal authority for licensing commercial activity in space, and a commerce-focused study of the commercial potential of space solar power. So I heard back a lot of great feedback, that they were very well received from the members of Congress. And it's just a great event if you've never experienced anything like that before. But that's what we're doing within the NSS. We are promoting an awareness of space development and space settlement, and also creating the interest and hopefully pushing forward the ideas and the work that will get us to become a spacefaring civilization. The last thing I want to mention is something we just started this year. We have our office here at the Kennedy Space Center in Florida, and we actually did a members tour of the Kennedy Space Center and Cape Canaveral Space Force Station. So we are going to be doing another one. This last one was held in January. We just settled on the dates. So it's going to be Friday, September 20th through Sunday, September 22nd. Really great tour the last time around. Obviously seeing great things like the space shuttle and the Saturn V, the VAB, going out to the Cape Canaveral Space Force Station, and that's the lighthouse at Cape Canaveral there. So look for more details soon as we start doing the planning for this. We had a great time this first time around, and we're looking forward to a second round. So with that, I want to just finish up with the intros for NSS, and hopefully we'll see you at some other future events as well. So it's my pleasure now to turn this over to our HAL 5 hosts. So Ronnie, are you good? Ronnie LaJoy from the HAL 5. There we go. Hey, Ronnie. Sound is not good, Ronnie.
It's Tim Weaver. Tim Weaver is going to do it.
Oh, there we go. There we go.
Yeah. Okay.
Okay, Tim, you're on.
All right. Thank you. My name is Tim Weaver, and I'm the president of HAL 5. That's an acronym for the Huntsville, Alabama L5 Society. We're a chapter of the National Space Society. It was founded in 1983 as a chapter of the former L5 Society, which was founded in 1975 by Carol Manell and Keith Henson to promote the concept of humanity living completely off-world in large rotating habitats as a vision by the late physicist Gerald K. O'Neill. In 1987, the L5 Society merged with the National Space Institute to form the National Space Society, which has a much broader vision of humanity's future in space. Our guest tonight is Dr. Jason Cassibry, professor at the University of Alabama in Huntsville. And the webinar is titled Experiments, Modeling, and Theoretical Efforts in Fusion, Artificial Gravity, and Breakthrough Propulsion at the Charter Advanced Power and Propulsion, CAPP, Laboratory at UAH. Also, I would like to encourage you, if you're not a member of the National Space Society, or HAL 5, to sign up. We have applications at the back, along with free samples of Ad Astra, which was mentioned earlier. Right. Take it from here.
All right, thank you very much. Thank you, Tim. He was an excellent student. I think he took just about every grad course I ever taught back in the day. So anyway, and another person a couple of people I want to call out. My mom is here, so it's good to see her here joining us this evening, and getting a little bit of feedback. So I may or may not keep using this. We'll see. And anyway, I also want to call out this young man over here, John Cole. He was one of the reasons that I'm actually here in the first place. So he was instrumental in supporting advanced propulsion, and he helped me many different times when I was a young kid, coming to save the world with all of our ideas for advanced propulsion. And he had a great unparalleled program in supporting advanced propulsion for a number of years. And really, there hasn't been anything like that since you left. So you need to come out of retirement, go back to NASA, and get that started again. Oops, sorry about that. So anyway, let's go ahead and get started. So I inserted the word fission into the title because I didn't think we had enough topics to discuss this evening. So I wanted to add it in there too, mostly to acknowledge the work that we're doing with NASA on a fission concept. So let's orient on dimensions first. So time. So we use the second as our basic unit of time. Where does it come from? So 1 second is defined as the fixed numerical value of the cesium frequency, the unperturbed ground state. Oh shoot, this is getting in the way. Let me get that out of the way. Hyperfane transition frequency of the cesium atom, and I think that's about 9.19 gigahertz, where 1 hertz is equal to 1 second. That's where the second is now defined. Everything else is derivative of that. 1 hour is 3,600 seconds. A day is 24 hours. A dual linear is 365.25 days. And better than 1%, 1 year is approximately pi times 10 to the 7 seconds. If you're trying to ballpark something, and while your friends just keep that in the back pocket. So now let's talk about length. So length is actually defined based on the speed of light now. So 1 meter is the distance traveled by light, and 1 over 299,792,458 seconds. And meters are used, to measure spacecraft and launch vehicle scales. We use the foot and the kilometer, and then there's the astronomical unit, where that is about 1.5 times 10 to the 11 meters, roughly the distance between the sun and the Earth. And so for solar system scales, an AU is a very convenient unit of frequency. It goes from about 0 out to 100 for most of the things that we deal with. And there's a more precise definition for an AU, but let's not get into that. So on galactic scales, the light year is what we tend to use for the measurement. And I don't recall how many meters that is. I should have put that in scientific notation. But it's the distance that light travels in a year. And these are huge, huge distances. So our galaxy is about 100,000 light years across. In 1 nanosecond, light travels about a foot through vacuum. So in 1 nanosecond, 1/1,000,000th of a second, light goes about this far. A parsec is another thing that you hear. The Millennium Falcon, of course, that's scientifically based. When did the Kessel run in 11 parsecs or something like that? But the way it's defined, it actually has to do with astronomy. So the Earth's rotation basically factors into that, and it's an angle. It's one AU sub 10 is the angle of 1 arc second, and the parsec is defined based on that, and it's 206,000 AU, or about 3.26 light years. So if you hear parsec used, that's where that comes from. So now let's get to the fun one, velocity. So we start with meter per second. So we've already defined what meter per second is. A mile per hour is about 0.447 meters a second. If you're trying to do this in your head, just take miles per hour and divide by 2, and you get pretty close. A kilometer a second is starting to think in terms of spacecraft for missions to the moon or missions to Mars and things like that. Those are kinds of the speeds that are involved. A little bit more than that, but that's getting close. So 1 click, another reference point, is 1 kilometer per second. That's about Mach 3. 7.5 kilometers a second is about low Earth orbit velocity. It's about Mach 23. The speed of light is about 3 times 10 to the 8 meters a second. That's the speed of light in a vacuum. And that also corresponds to about Mach 1,000,000. So if you're flying in the Earth's atmosphere at Mach 1,000,000, you're going the speed of light. You're also vaporized, but they should have a little claim to fame there. So now let's get to science fiction, and then we'll get on with what we're up to at UAH. So warp speed in Star Trek. So the way warp speed works, so there's a physics basis for it. It's not been demonstrated experimentally yet that I'm aware of. But the basic idea is that you can warp or distort space-time where you contract it in front of you and expand behind you. And we now know that space actually can expand faster than the speed of light. We can physically observe that. It doesn't mean that we can travel faster through the vacuum, but we can stretch and expand the vacuum of space and cheat and go faster than light that way. So that's our hack to get through space-time if we can actually achieve that. So what does warp drive mean? So next generation all modern content 1 to 9 is given like roughly warp to the warp to the cube, or warp cubed is basically the answer. And then there's all kinds of different variations on that. Hyperspace, which is in Star Wars, is a lot faster. And hyperspace is defined according to the screenwriters for whichever movie TV show is out. So it moves as fast as the plot is needed for the script writers to advance the story. That's a quote. But to ballpark it, so galaxy has a diameter of 100,000 light year, and it takes a week to cross the galaxy. That gives you about 5 million C for hyperspace travel. And then there's one more, the most important one is ludicrous speed. And that's, if you go ludicrous speed, you know that you go to Plaid. And it's about 1000 C or roughly warp 8. And that's according to the peer-reviewed Reddit article that I could find to provide a definition for it. So there we go. So there's all that, something to shoot for. So who are we? So the Charger Advanced Power Propulsion Laboratory is part of the Propulsion Research Center at the University of Alabama in Huntsville. So we're really good at smoke and fire and blowing smoke everywhere. This is an example. This is our supersonic wind tunnel over here. It's one of our facilities. And it's really just all about the people, the past, present, and the future, the students. We're here to train the students and help them go out and have exciting careers and help solve the next generation of problems. So, but the thing that gets me out of bed in the morning is the excitement of working with fantastic colleagues like Dr. Judy Schneider. Oh, you're here tonight. Oh my gosh. Wow. That was lucky of me, right? Okay. And second to that, it's the following. So this is the Flint River. So I'm not excited particularly about a random river, but just as a reference point, this is in Tennessee and in Alabama. And it flows about 2,000 gallons per second. There's enough deuterium in the water. So water has this tiny fraction of the hydrogen in that water is deuterium. And there's enough flowing through that river to sustain 20 terawatts of fusion power. So if you could burn it all, just that one river could power the entire world with what we draw on electricity right now. And everything that contains water, rivers, creeks, ponds, lakes, oceans, running faucets, clouds, plants, animals, they all contain deuterium. And if we could figure that out, we could figure out how to crack fusion. It just about democratizes energy because you've got water all over the planet to be able to derive the fuel for creating electricity. So, but what is fusion? So fusion is when you combine the light elements together and then they make new elements and release a massive amount of energy in the process. So the easiest one to do, and I put that in big quotes, is deuterium with tritium. So deuterium is hydrogen and tritium is just a heavier isotope of hydrogen. When they merge and fuse, they release a neutron and a helium with a lot of energy. And so this is kind of the basic idea. Now, I think I've had the honor of doing a How Talk. This is my third trip here. And the last time I was blabbing about this giant pulse power machine that we had that I was so proud of. And so now let me talk about a colossal failure, okay? And what we learned from it. So we had this opportunity to get a pulse power machine that was a leftover from a nuclear weapons effects program. The program was called the Decade Quad Facility, which was up at Arnold Engineering Development Center. We had the last prototype that was built before they cloned it and took 4 of them, connected them together, and had one of the largest pulse power capabilities in the world at the time. And we were like, yeah, of course we want this machine, absolutely. So we collaborated with Boeing and brought it in and worked with NASA for about 8 years, and it was a lot of fun. We learned a tremendous amount on the job. And this is some of the original group right here, assembling some of the machine. And this is one of my former students, Dr. Ross Cortez. But what happened is, so we collaborated with NASA on this, and it led to working on something called PUF, the Pulsed Fission Fusion Hybrid concept. And we spent a number of years trying to figure out how to make that work and understand all the physics. And it possibly could lead to a much smaller propulsion system because of the coupling between the fission and the fusion and how they kind of can help each other. As we got into the physics to figure out what was required, we decided to reach out to the Department of Energy to say, these are the calculations that we're doing. Can you help us vet this and collaborate together? and they looked at the codes and our calculations and what you guys are doing a really good job. Now you have to stop it. So between that and then a tri-agency agreement to stop doing fission fusion hybrid stuff as part of their advanced propulsion portfolio, that kind of killed that whole effort. So that sort of forced us to stop all of this effort. And so then I was stuck with, okay, I've got this giant machine. Now what do I do? You know, if we can't go that direction, and this machine was very, very complicated in the first place, what can we do that's additive diffusion that might make this easier to do? So I started doing some calculations, and I literally sat down in a chair in the middle of the lab going, okay, how do we dig out of this? And so I started doing these power balance calculations. It's just thermodynamics 1, basically. And what you're looking at on the x-axis is number density. So the air in this room has a number density of about 10 to the 25 particles per cubic meter. Let's count them together. Okay, no. The y-axis is temperature, and it's in funny units. It's in kilo electron volts. 1 electron volt is 11,605 Kelvin, very, very hot. At about 1 EV is when you start to get ionization of the atmosphere. So things that come through reentry are of temperatures of the order of 1 to 2 EV as they enter Earth's atmosphere. And it's because of that ionization that we have that communication blackout during part of the reentry. So, but anyway, what this is saying is that if you have a fusion plasma, and you're trying to burn it, if you have no implosion velocity, but you can have all the temperature that you want, there's this little space over here, if your plasma is small, like 2 millimeters, for example, that actually burns. This is where NIF lives. This is the National Ignition Facility where they're getting all of the headlines. So their densities are about 100 times solid density at peak compression. So just tremendously high pressures. And this is without any magnetic field. And this is this color over here is colored on energy. So how much thermal energy is actually in that plasma? And so like over here, just a 2 millimeter plasma, basically just like a little BB, has some maybe 10 gigajoules of energy in it, or just the NIF actually isn't that large. It's more like a megajoule, but just, you know, just think how much energy is packed, thermal energy packed into this little target. So I said, okay, so let's crank up the magnetic field and see how this space opens up for us. Because as you increase the magnetic field and increase the implosion velocity, what happens is this boundary that you're looking at is telling you the blue region is where it cools off. That's why I picked that color deliberately. Blue is going to be cold. Anything else warms up. And this dashed boundary is where it means that you can get into fusion relevant temperatures. It's a really, really hard part about fusion is getting to these high temperatures. So if you can crank up the speed and crank up the magnetic field in the target, you can start to open that space wide up. And so I realized, wait a minute, I could, instead of having these really exotic large machines that have pulse compression in order to try to get to these high density regimes, which is what we've been shooting for years, when we started rethinking this, like maybe we could get to just really high magnetic fields and go in a much lower density regime. And so once I realized that and I started calculating how much energy is in that system and just kind of playing with the numbers, I realized that we could kind of operate in a real hybrid between magnetic fusion energy like tokamaks and the extreme inertial confinement fusion, and possibly have a small scale reactor that breaks even. And so that's what we're working on right now. That's kind of what we're trying to develop. And so a lot of what we're going to talk about today is kind of some of the tools and the things that we've done along the way towards that goal. So one of the things that just pains me is the joke, fusion is the technology of the future. It always will be. And it is frustrating because it's true. I've been working at this for so long, you know, and my part of it is small compared to the whole history. But if you plot all of the progress on one chart, you can see that we're actually marching towards break even. We're actually tracking better than Moore's law in terms of how much energy output is coming from these reactors. So if you go back, this is where it got declassified and people started working openly on fusion. So right here around 1958. And then you have all these different experiments that came online and marched forward. And here we are in 2024. So this picture here was generated in 2020 by Sam Wurzel and Scott Shue, who work at Department of Energy and help come up with the policies for the nation on fusion. And so they published this. Dr. Shue is the lead fusion coordinator for Office of the Undersecretary for Science and Innovation at DOE. And so this just kind of shows the rate of progress and how things are going towards break even. So you can kind of forecast we should be there in the 2030s. So we're getting really, really close now, but we have to work really hard to make sure that these trends continue. So we'll talk about what we're going to be doing within that. But things are changing very, very quickly. I made this chart just a year ago where over 35 fusion companies had formed, and there was almost 5 billion in investment. And now I've lost count of how many fusion companies are out there. There's, I think, somewhere around 70, maybe. And so there's, I think, a few billion that have been thrown in on top of this private investment. So things are changing and progress is being made very, very quickly. So it's an exciting time to be in it. So some of the prominent companies that are out there, you've got Commonwealth Fusion. So of that 5 billion, I would say like 30% of it just goes to this one company. They have a tremendous amount of investment, but they have a lot of credibility behind their concept. And so what changed and enabled them to do this is a similar failure. They were part, this is an MIT group that have always been part of the magnetic confinement stuff. So tokamaks are basically like magnetic donuts. So the plasma is in basically a donut shape. And so when ITER, the International Thermonuclear Engineering Reactor, was starting to be built, all of the money, most of the money that went into our fusion program started to go to that. And so a lot of the domestic fusion participation went away. The budgets were zeroed out because we couldn't afford to do that and everything else that we had. And they didn't want to get out of the action. So they scratched their heads and started thinking, well, what can we do? And they actually worked on superconducting magnets and helped develop the technology to lead to magnets that could get to 20 to 40 Tesla at pretty high temperatures. And so they completely revolutionized superconducting capabilities because of that, because they were motivated. And that now leads to a smaller reactor. And so now they've got a lot of investment because of that hard work. Helion is, so they're in Massachusetts. So Helion is on the other side of the United States, up in Washington. There's, I think, a half a dozen fusion companies up there. So I don't know, maybe they got extra deuterium in the water that motivates them or something here. Have a little deuterium myself, hang on. Okay, better. So anyway, Helion is probably, oops, I gotta stop doing that. Helion is probably the largest company in fusion on the West Coast, and their concept, they form a plasma, kind of a donut like a tokamak, but it's a pulse system. So they form it, they shoot it into this little chamber, and then they compress it down with additional magnets. And so they're making some very interesting progress, and they have their own what they call capacitor kitchen, where they cook up new capacitors to help with this. So they've got a really well-funded program. This is just a roadmap. I think I'm going to skip this and kind of get into the portfolio and what I'm interested in, actually. So the fuel sources that people propose are all over the place. Most of them are deuterium tritium. So of the 35 companies that I had listed, statistically, 22 of them were doing deuterium tritium. 5 are doing p-boron-11, and then there's a mixture of deuterium and p-boron-11 and d-helium-3. The reason the deuterium tritium is picked is because it's the easiest fuel to burn by an order of magnitude. And then p-boron-11 is not a close second, but has the next highest level of participation, is because it doesn't make any neutrons. Neutrons are terrible. You burn a plasma, it makes neutrons, and all those great materials that you came up with slowly start changing over time. Like sometimes they crack because of neutron embrittlement, and sometimes they turn into different elements because the neutrons will transmute and just change it into something else, and they can make it radioactive. So neutrons are really hard to deal with, but p-boron-11 is so hard that I'm not sure that anyone's really going to get there anytime soon with it. So, but we'll see. I'm glad that people are working on it. So what are we doing in fusion? So our main efforts that we've been involved in recently, plasma jets driven magnetoinertial fusion is one of them. And so this is a collaboration with Los Alamos, Hybridjet Fusion, University of New Mexico, and Spaceway, which is a company in Florida. And it's funded by Department of Energy, ARPA-E, and NASA. And we have this cartoon down here that shows, this is actually a simulation that we did, which is prototyped on this machine, actually, right here. And we have a three-dimensional implosion of 36 plasma jets and 6 jets that are magnetized by those external solenoids. So the field lines that you see, the blue things are magnetic fields, and you can see as the plasma comes in, they're conductive and it distorts that field. So it sweeps up the magnetic field and compresses it. And that's one of the merits of magneto-inertial fusion, is that the field acts like an insulator, trapping the electrons, which release the energy otherwise. So that's really important. And it took us about a decade to develop a code that could do these types of calculations on a machine this small. So this is like in the last couple of years, this is sort of a new capability that we've had, but it's taken a tremendous amount of work. And a lot of grad students sweating with me over trying to get this functional. So the other company that we work with is Near Star Fusion, and this is a hybrid of gradient field and impact diffusion, and it's derived from actually a NASA propulsion concept. They're based in Virginia, and the funding so far has come from Department of Energy, the state of Virginia, private investment, and National Science Foundation. And the basic idea is they have a rail gun that shoots a projectile up to about 10 kilometers a second. It runs into a chamber, and the details of what happens in that chamber are proprietary. Pretty cool. We're working on it. I can't say much more about it at the moment. But this is something I'm very, very excited about. And we're hoping to make a lot of good progress on that this summer. So when we can talk about it, and we get good results, you'll hear from me. So now that takes us to our next step. So we had to move out of the lab on the Arsenal because SMDC took over the building and their priorities shifted. So we're like, okay, we can't squat here anymore. So we moved what we could up to campus and decided to focus on smaller, slower, simpler machines. And the main machine that we focused on is this mobile thing that the kids named Sparky. So Sparky is a 60 kilojoule, 40,000 volt capacitor bank. And this machine was, so this room was supposed to be a room intended for, I think it was like kind of like a medical center or something. Did any of my students know the history? Yeah, I don't really know what it was for, but they were going to condemn all of these buildings and start doing major construction. And then the pandemic hit and halted it. And so we basically got to work in a condemned building until the pandemic lifted. So, you know, you mix feelings. You don't want to see everybody get sick and all of that, but it was nice to have the building for a while. So we moved our entire lab, or most of it, up to here for about a year and a half. And then we had to move again to our more permanent home. But along the way, we picked up a very interesting project in fission, which is why I added fission to the title. So this is a CAD drawing of an experiment called the ant farm. And when we started doing this, and people say, what kind of work are you doing? You know, if we're at a restaurant, I'd take my straw, put it in the water, just blow bubbles and say, we're doing this for NASA, you know. So what is it actually? So it's derived from any great idea you had was thought of in the 60s and 70s, I'm pretty sure. So this is a liquid molten state uranium nuclear thermal rocket. And so the idea is that you have a bunch of these cores that are spinning to centrifugally confine the uranium. And the point being, the hotter the temperature, the faster the exhaust velocity of the gas. So you can say travel to Mars faster or travel with higher payload mass fraction. And so they decided to resurrect that and start funding it. And so we had the pleasure of getting to work on it. So this little spinning animation here is basically one of the possible fuel elements. And so there's two variations that we're looking at. One in which each fuel element is sort of separated and it's an individual element with its own nozzle, and another one in which they're common and then they all go through one nozzle. I'm not really sure which concept's going to win yet. So we have to understand how the hydrogen can bubble through that liquid uranium and then go out into a nozzle. And this is harder than the fusion stuff that I do, trying to get all of this to work. So the first thing that we did is we tried to duplicate the work that they had in the ant farm. And there's a young gentleman hiding back there who successfully was able to benchmark code against that. Oh, good. It's embarrassing him. Good, good. Then next up, there's a new experiment that they're developing called the blender, in which they basically take the ant farm and they spin it up to 7,000 RPM. They don't have it spinning that hard just yet, but they're getting there, and they're going to feed the gas sideways as a way to kind of approximate that spinning cylindrical drum. So we modeled that, and this is probably the single hardest model we've ever developed. Is trying to come up with a planar enclosure and a liquid inside and modeling the liquid with bubbles coming into it. We're working on that right now, but so far we're doing okay with it, and the liquid is separating out and going up the walls, and haven't really gotten into tracking the bubbles yet, but that's part of the progress. And then we're also doing the cylindrical one, in which you see here, this is like a subset version. And so, but anyway, we've got it working. We just have to make the physics better, but that's where we are with that. We're one tiny part of a huge national project on that. That's kind of exciting. And so this was last year's Nuclear and Emerging Technologies for Space picture. And so here's some of our grad students. And I think, oh, no, I'm here. I thought I was going to not be in this picture, but yeah, I'm there. So, okay. So now we moved out to the airport. I think when they realized we were trying to do fusion and nuclear reactions, they said, yeah, let's move you a few miles away from campus. There just really was no space at UAH for all the equipment that we had. So we moved us out to a Hexagon-owned facility, and we're about to renew our rental out there. So we're very excited. So we got our own mailbox, and we felt like we made the big time now. And this is basically what our lab looks like. So we have these pallet racks to kind of hold most of the equipment that we have. And so that actually takes up quite a bit of space. And so here's Sparky. Sparky has been moved over. And thanks to a lot of our students, and I'll say the lead on this was taken by Jacob Kinsey and Logan Towers on getting this machine operational in the new facility. I think Logan is here with us today. And Logan just got his master's thesis defended on the machine. So we did a number of shots with the machine, and we did one where we said, let's try a lithium deuteride just to see what happens. Because our instrumentation wasn't quite ready yet. But we did a shot, and we measured before and after with the background, and we did slightly activate the chamber. It seemed like, so we kind of did something. It's very, very safe. We have a lot of safeguards in place and detectors and things. So we didn't do any harm to anything, but we think we actually did real fusion for the first time here recently. But now that we think that we can do that, we're going to be a lot more rigorous about everything. So we're developing our diagnostic system and trying to come up with a better source. And we're working with the radiation safety officer. So we're very excited about this. And so we also have an assortment of high voltage equipment. This is a Tesla coil that we have firing, and we took the dome off of it, obviously for no reason other than just to make cool sparks so we could have a picture. And then we're refurbishing these high voltage power supplies that will take us from, we can go to 0 to 60,000 right now, and with the yellow one we can go to plus and minus 100,000. So we're working on that. And this is most of our team. We've got a few new people that have been added. One or two of them are here today, I think. Hey, how you doing? But anyway, this is a lot of our team right now. So, questions so far? Okay, thank you for not falling asleep just yet. Yep.
Does it matter which direction does the liquid you'll set up the drum? Does it matter which direction do they go in?
So I think yes. I think you have to counter rotate them in an even number, because I think it'll have a torque on the vehicle otherwise. And if you have an odd number, I'm not exactly sure how you deal with that. So there's probably going to have to be some kind of control system in order to counteract that, or somehow way to spin all those different ones. That's not something I'm particularly concerned with, but that's absolutely going to be an issue. Yeah, yeah, yeah. Astronauts take issue with the unintended spinning of the vehicle. Free gravity, you guys are welcome, you know. Yes,
I'm still wondering how the Fusion project got pulled away. I'm reminiscent of Dr. Cole's work back in the day, when they were trying to do antimatter, and everyone was worried there's gonna be a black hole generated and we'll all disappear here in Huntsville. Remember those days? Okay.
Yeah.
I came out to your lab and visited, and I thought it was fascinating working at you. So now I see this cool project you're doing, kind of going away. Can you give us a tidbit of what the sensitivities are to that?
sure. Okay, so I'll have to redact certain things, but, okay, so the idea behind the fission fusion hybrid is that if you get the fusion part burning, like fusion is very rich in producing neutrons, right? And so, while fission is kind of poor in producing neutrons, you have to do a lot in order to manage that budget. And so if you can get the fusion to burn and generate neutrons, then if they couple into the uranium or whatever material, we looked at other materials as well. I'm sure as we Googled it, we got on somebody's list in the process, but so the fast neutrons will fission with both uranium 238 and 235. They have cross sections to burn both and release a tremendous amount of energy. But you have to have a pretty long distance for those neutrons to travel through solid in order to get them to actually burn, have a good probability of burning. So in order to get around that and have a smaller pellet, you've got to compress beyond solid density. And that gets you to, can't finish the sentence, but that it gets into an issue where it runs too close into other applications. And at the same time, the energies required to achieve that turn out to require a huge pulse power facility. So you lose the ability to shrink it down because you have to compress the solid it's hard enough to compress any solid, but the farther you go up on the periodic table, the worse it gets. Because there's just this huge electron cloud and you push on it and all those electrons are kind of pushing back and it just makes it really hard. Makes certain properties go up very, very quickly. And so you just can't deal with it. So we didn't really lose out on some big important, I mean, it was a great project, but there's other ways to do basically that same thing. And we think we have a better path now to make it smaller, but we wouldn't have known that had we not spent all that time going through all the math and all that. It's closely related to like Orion. I'm sure you're familiar with Orion, and Orion they didn't want to do either because Orion is a concept in which you would detonate atomic bombs, and there's almost no better propulsion system out there. But you have a nuclear fallout every time you do a launch, or if you just take it all to space and do it from space, it would take a lot of launches to assemble that vehicle. And now you would have a bunch of bombs in space. And so if we did it, we're like, well, this is just for science. And other countries would go, yes, us too. This is just for science. And so then we would have this big arms race, and nobody wants that. And so it's just politically a non-starter for that reason. And puff is not, you can't really weaponize the puff concept, but it's in that family of things where politicians go, ooh, I don't want this. Yeah, so that's kind of what happened. Question, yes, blue. Oh, sorry.
What is PB11?
P for protons, hydrogen, and B11 is boron. Okay, so it's one of the, so boron, which most of your laundry detergent has borax in it, and so that's, I forget the levels, but boron 10 and boron 11 are both really, really common isotopes, and they're found in laundry detergent. I'm getting some kind of weird feedback. Okay, that's better. Robin, did you have a question?
Yes, I did. I was wondering, what is the energy range of the neutrons? And have you noticed the minimum energy that causes damage to the materials?
Very good question. And for fusion, the deuterium-tritium reaction makes a 14.1 MeV neutron. So it's a massive amount of energy, and it'll dislocate up to 50 atoms in a lattice typically. So it does a lot of damage. The next one down for deuterium, it makes every other reaction that occurs is 3.5 MeV. It'll make one of those, and it'll still do damage. And then at low, and so the absorption cross sections typically are much lower energy, so they have to be moderated first. And at those lower energies, then it can basically transmute elements. And so any system that you have has to be designed to account for that, knowing that the neutrons are going to walk their way in and then get absorbed into stuff and change the contents. And so the way we handle it in our lab, let's see. Oh, here we go. Okay, you see these little blue containers? So they're filled with borax. And then once they're full of borax, you pour water in and get it as dense as you possibly can. And Mr. Thaggart over there is laughing because he's the one that actually poured the borax in for most of them, I think. And thank you, did a good job. And so what happens is that the neutrons come out, they get scattered and attenuated by the hydrogen, they slow down, and then they get absorbed into the boron, and then they react and form a new component, which is stable, but then they release a gamma ray when they do that. So you have to shield for the neutrons with hydrogen, and then you have to shield the secondary gamma rays with lead after that. So the shielding is very, very complicated when it comes to neutrons, as you know. Good question. Other questions before I move on? Yes, yes, sir.
Company is using a lithium blanket,
Mhm.
a liquid lithium blanket rotating around much as you're playing the uranium still inside the drum, and they're using that as a neutron shield. Have you looked into that? Is that something that's feasible?
Yeah, you're talking about a lithium blanket as a way to, I think what they're doing is using the lithium to shield the neutrons and then generate tritium from that. Because tritium is a really important fuel, but it doesn't exist naturally. You have to breed it. So reactors would basically are designed to try to breed tritium and then recycle that tritium back in. And so I think you're talking about first light fusion, and what they have is
General fusion.
general fusion. Oh,
Yeah.
oh, that's different.
They're the ones doing the steampunk concept of using pistons
Yes.
to compress a plastic.
Yeah, they are actually one of the very first private fusion companies. And so in their concept, they use explosives to drive these metal pistons to compress and magnetize target. And the piston serves two functions. One is to compress the target, and the other is to also breed tritium and shield against the neutrons. And so, yeah, that's what their concept is. And it's rooted in another concept called Linus, which existed years before that, mostly just on paper. But you can look up Linus or general fusion and kind of get the gist of what they were doing with that. So let's talk about why we should go to Mars. So I always like to share this, give an advanced propulsion talk, because like a lot of times when you hear talks on advanced propulsion, people kind of give those mom and pop, oh, it's inspiring, you know, we got to do this. But the reality is it's very expensive. And so you need some real substantive reasons to give to politicians so they can figure out why to spend money on your thing instead of something else. And so really it comes down to, if you want to study something like Mars, it's hard to beat the human brain. It's really what it comes down to. So humans are basically, our brains are like 20 petaflop supercomputers, and they only need about 100 watts to run. I mean, there's nothing that comes close to that capability. So a lot faster speed and efficiency to optimize field work. And we have the agility and dexterity because we have hands and things to do things. The on-site team can overcome communication problems. Is everything okay? Or...
Yeah,
okay.
well, I think what happened is when we had Bert speaking.
Yeah.
I think we switched the source of the mic.
Oh,
Zoom.
okay.
So
Okay, just make it
that's easy to
sure.
switch back and-
So there's a communication lag. So if you go to Mars, depending on where Earth and Mars are, you've got between 6 and 20 minutes communication transit time. So it's really hard. You can't just do stuff. You can't say, hey, why don't you go look at that rock over there? You've got, it could be 40 minutes before the command is issued versus, what they do. So you really need some autonomy. And so it really helps to have people. So that's kind of one of the things that motivates me in terms of crewed space travel and how to make it better. So here's our neighborhood, and I've put it on astronomical unit measurements because remember I said earlier the least scale that we think of for the solar system is 1 AU because Mars is like a half a AU away from us, and then Jupiter is about 5 AU out, and so on and so forth. And just look at this. So we've been to the moon and we're going to go back soon. And that's only 0.001 to 0.002 AU out. So we're just barely, it's so hard to do that. And we're just barely scratching the surface of exploration beyond Earth. Most of what we do is in that tiny little cyan colored circle right there. And pretty soon with Artemis 2, we're going to send people back, not to land on the moon, but at least to circle out and go this way. So it's very exciting to get to do that. But then we look at the scales, we see if we put this on a log scale. So here we are at Earth, and we've got this huge region that we can explore. This is our nearby celestial neighborhood. And these are all the worlds. And this is another thing that really strikes me. So we get excited about Mars, but I also think a lot about all the other worlds that are about the size of the moon or a little bit smaller. Most of them are kind of far out. Most of them are cold, and they have a gravity that's about 10% of our gravity. And there's many of them to go visit. And I think about this a lot because I think about, what could we do on those planets? Could we dwell there? Could we do things? Could we, is there value to it? Probably, maybe not at the moment, but I do think a lot about these as maybe not Mercury. That one might be a little toasty for us, but the rest of them, I think about the possibilities of visiting some of these other places and what might be there. So I did this calculation for this talk. This is a walkthrough of the solar system. I did this 2 days ago. And so you can kind of see as we zoom out just to kind of get a sense of scale. That last orbit there was Sedna, which has a huge orbit of like 3,600 AU. And now we have the Oort cloud coming in at about 100,000 AU. Now we have the nearest stars. And then we see the ones that were sort of highlighted here. Those are the habitable ones. So we have actually a good number of stars in the habitable zone. But now let's look at this chart and figure out what technologies to get to all these places. So on the y-axis, we have delta V. That's roughly how fast do you need the spacecraft to go? And on the x-axis is the energy density of the fuel needed in order to do those missions. And this blue line is just an approximation, but it really does capture a lot of physics this way of how fast the exhaust velocities need to be coming out the vehicle in order to practically do that mission. So in other words, you could use the chemical propulsion system and go to the next star, but if you try to do it fast, you're going to have like a postage stamp worth of payload in order to get there, or you're going to have a very large system. So you really need an exhaust velocity that's comparable to the delta V, and that's the assumption in this curve. So let's start at the bottom. Lunar round trip in a week, we can do that. That's chemical propulsion. If you look at the intersection here, chemical energy density is around 10 to the 7 joules per kilogram. Mars round trip in 2 years also can be done with chemical. It's pushing the limits, but you can stage things and put things out at the destination and refuel there maybe and kind of help close that mission. It starts to get easier if you start looking at nuclear technologies though, because you have better energy density, you have a higher specific impulse. And so now you really kind of need something that can give you about 1,000 seconds ISP to do that. Mars round trip in 6 months. Now you're talking, you need at least 2,000 or 3,000 seconds ISP. Now you're pushing beyond the limits of nuclear thermal propulsion. You need something better. You need nuclear electric if you could get the size of the electric system and the radiators down, or you need fusion. And then you start pushing out a Titan sample return in 2 years, a heliopause flyby, Oort cloud, gravitational lensing in 10 years. And all of these need enormous specific impulses like 10,000 seconds, 100,000 seconds. And simultaneously, it needs energy densities that keep going up and up and up in order to do that. And so nuclear can kind of do some of this. fusion, so nuclear, a lump fission and fusion together, but fusion of the two of them can really give you higher specific impulse and good thrust, and the delta V in order to get there. So it kind of gets you here. And then there's a gap of, there's not a lot of missions that I'm aware of that we could do here that have a lot of value, and until we start looking at the next stars. And even with going to stars, we're really pushing fusion's limits at this point. Like you could maybe do something in 50 to 100 years. But in order to really do it like that, you'd have to stage it. And I hate to throw away a perfectly good fusion reactor, but you know, if we must, but it really kind of becomes impractical even for that. So you have to kind of look to things that are more exotic, like antimatter, laser, light craft, if you can make that work, or warp drive. So now let's back up. Let's change gears and talk about something else that interests me, and that is the microgravity environment. So we've kind of got that managed, but what astronauts have to do is they have to work out for 2 hours solid a day in order to keep from really deteriorating too much due to the microgravity. So it's a solvable problem, at least for a year. But now if we look to going to Mars, what we're worried about is once they get to Mars, are they going to have therapy on the site before they can really do their work? You know, we don't know, but we know that the health risks in being in microgravity are pretty significant. The bone loss, the muscle weakening, cardiovascular conditioning, etc. And so if we can do something about that, I want to. So these arguments here actually came from Dr. Torrin Clark, who does anti-gravity countermeasures. They have a centrifuge out there, so they do a lot of research in that area. But we came across something else that we realized we could leverage all of our pulse power supplies to do. And that is using something called dielectrophoresis. So what is that? I've worked on it for a number of years now, and I still need Google's help to spell it right. But basically what it is you have a gradient in an electric field. Okay, so you take a power supply and literally just here's an electrode and here's another one. Let's make one flat and one of them small over here. And you can see how the field lines kind of coalesce to a point. So there's clearly a strong electric field gradient. The lines of force are tighter over here than they are over there. What does that do? Well, what happens is the molecules, everything can be polarized. And so let's say the field lines are left to right, and the molecule or the atom orients itself so that slightly more field or slightly more of its charge is attracted to the stronger side of the field. And it's sort of like a tug of war, and this side wins. And so it always tends to go into the direction of the stronger side of the force. There are exceptions, and the young gentleman that I was bragging about earlier that did the modeling of the bubbles is also my foremost expert on dielectrophoresis and all the exceptions to the rule. So he's I'm not going to be able to get rid of him anytime soon. But some of the applications of dielectrophoresis are mostly on the small size, the particle size, and medical applications. And it's really neat. They use hundreds of volts in these small scales, and they can separate cancer from regular tissue or bacteria from cells and things like that. It's really cool what they can do. And I found out about this, and I said, oh, they use hundreds of volts. I wonder what you can do with 40,000 volts. And actually, there was an aerospace application of this, and I found the paper and I read it, and it said the author was Jim Blackman. And Jim Blackman literally was my office neighbor 2 doors down, and he doesn't know when to retire, so he just keeps working, as a lot of us do, I think, in Huntsville. So I went and talked to him about it, and he had a lot of great things to say. But so during the pandemic, this is when I thought about it, and as one does, for your birthday, you treat yourself to a high voltage power supply, and you set things up on a ping pong table because, you know, I had free time. This is dangerous things that happen. And this is not a very good movie, but this was one of the first things that I got to be successful. You see, that's a ping pong ball. And what I was able to do was to pick up the ping pong ball, and the marble did a strange thing and kind of wandered around, but I was able to figure out how to set up something to lift it up. So the rod here was at 1 voltage, and then the aluminum foil at the bottom, I think, was at ground, and that's what I did there. But it worked. If you reverse the polarity, it would still pick it up. And so I thought, I think we have something here. And then I tried a lot of other weird things like just the rod by itself. And I tried to set up something that I could see if I could just tilt something over because I couldn't pick up things in general. And so there's a rod here, and then this is insulated by there are these blue PVC pipes you can get at Lowe's. They're for plumbing, I think, and they just happen to work really, really well as an insulator. So once I kind of had a rough idea, oh, okay, we have something here. Then we started getting into trying to do something a little bit more rigorous with what we could do on a budget of basically zero. So we developed a 3D code to allow us to be able to calculate electric field. And this doesn't really mean a whole lot other than we've, have the ability to do that now. And that allows us to calculate the forces. And then we were able to come up with a stand that allowed us to quantify how much force, how much effective acceleration we could exert on different objects. And one of the things that was the most challenging about this is the arcing, because if it arcs, you lose the electric field, you're done, and it quits. So we had to solve that problem. And a student that has since graduated, her name was Savannah Flaherty. She came up to me one day, kind of sheepishly goes, "This might be stupid, but have you ever thought about maybe using art clay? Because we could try all these different shapes and just kind of sculpt things around it." I went, "Hey, let's try it." And it worked perfectly. So the next best thing is this high voltage putty, which costs 10 times as much. So this was perfect. We could go to Walmart and get all of it and bring it home and just sculpt these things, and we could bake them into ceramic parts. It was really, really, really neat. And so this is an example of one that I think either Savannah or Boom built. And so we put Velcro on a little wooden pole, and we tried marbles, wood, glass, clay, I think avocado, banana, chicken, just anything that we could find to see. And so we were able to actually generate about a third of Earth's gravity using a 40,000 volt power supply. So that got us very, very excited. And so now we're in the middle of trying to get to, we've written proposals, we're trying to get this funded, but we're trying to get to the point where we actually can pick up something large. So that's the goal. So to do that, we're going to have to get to well over 100,000 volts. And it gets a lot harder because the number of power supplies available get much more expensive, and the ability to suppress the arcing is a lot harder to do as well. So, but we're working on that, and that's kind of where we are at the moment. But our interest is in, can we make this safe for humans to serve as an artificial gravity environment? And so that's what we're looking at right now. And there's a lot of work that's done on that. Line workers are frequently around high voltage power lines, so they're in similar electric environments. And there's a lot of data that's available. It's not clear that this is safe or not yet. So an element of the research, I don't see us doing that anytime soon, but an element would have to be on making sure that this is safe for people. But so far, it appears that as long as you're at frequencies below 100 kilohertz, it's okay, unless you get shocked. That's a problem, and we obviously want to mitigate that as well. We have some ideas for how to prevent that. So that's one of the things that we're working on. We are going to present. Okay, I see. Okay, I see what just happened. I borrowed some old slides, and I think I had embedded recordings on that. So I thought I got rid of all of those, but I see that. I was like, how am I cloning myself? Where am I coming from? It's another, me from a different reality that's come to visit, I guess. Okay, so let's talk. The last thing I want to talk about before I get into the breakthrough stuff is the pulse magnetic nozzle work that we're doing, which is derivative of the pump stuff. So it's not dead. We're just doing it as pure fusion at this point. And so if you want to turn a fusion system into a propulsion system, for pulse, you have to figure out how to take an explosion and turn it into thrust. And that is very, very difficult because the plasmas are extremely hot. So the cartoon illustration of it is that you have a plasma that explodes into some kind of a magnetic field. These X's and O's represent coils that spiral around the shape of a nozzle. And the cartoon image has always been, okay, the plasma will do that, push the field out of the way and go out the nozzle and everything's fine. And the state of the art has been up to this point, whether you're modeling or experiments, that we know how to make a terrible, not working at all nozzle. So So it was only a few years ago that we were actually able to get our code to be able to do something and come up with a topology that would actually give us thrust. And then on top of it, this thing has to somehow produce electrical power to recharge the system for the next shot. So there's a lot of really complicated things that have to go on. So we came up with a model in which, let's say we take a little chunk of plasma, it runs into the coils. If it compresses that flux, so here's where the voltage is induced on those coils. It drives through an inductor, through a transformer, and then pulse recharges a capacitor bank. And so we're able to come up with a space over which we could do this and both recover enough power to recharge the system and get propulsion for travel. So it's very, very difficult, but everything, if you tune it just right, you should be able to get this. And this is just a model of what the current and voltage waveforms look like. And the capacitor bank, which had just done, in this case, it was a puff system where it delivered this huge amount of current to ignite it and create an explosion. Then the explosion comes back and runs through the circuit and charges the system to reset it back to 40 kilovolts again. So it can be done. And so now we're working with NASA on further modeling on this to try to improve it. And this is what we have at the moment. This is where we think we're going to need to go with this. So the coil is a hybrid of two things. One is windings that go along the length, and then there's another spiral. The spiral is going to be best for the flux compression to get power. And then the axial coils actually are what give it propulsion, what give it thrust. And so I have a little movie here of a simulation that we did where you can see how as the plasma explodes, it distorts the field and it's kind of coming out here. Now, in full disclosure, right after this, the code crashed. So, but we're making progress. We're going to, as soon as the semester is over and, they insist that I show up for class and blah, 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 grade finals and all that kind of stuff. But once that's over, we'll get back to working on this and trying to make improvements on these models. And we're working with Dr. Gabe Shu, one of my colleagues, and they're doing experiments. And so we're trying to duplicate their experiments and then scale it up to see how a full-blown system would operate. So we're really excited about getting to do this work. Questions before we get onto this? Yes.
Yeah. Well, I've heard that, sorry. Well, I know that NASA is also doing research on using, they're doing research on using fields to protect astronauts from radiation. And one of the ideas they came up with is a grid of basically a grid of statically charged points. Mm-hmm. And what it would do is take these charged ion particles and kind of nudge them in a basically, if it's coming right straight at them, you kind of nudge them off to the side so we miss the spot where the astronauts is. So do you see that probably as a possible 2-for-1 deal, artificial gravity and radiation shielding?
So I don't know enough about that radiation shield to answer that question. That's a good question. I don't know. I don't know how that works, like how they do the shielding, what the issues are. So if you email me about it, I'll look it up and tell you about it. Tell you what I think later. But that's a good question. I don't know the answer at all. Yeah, good one though. Any other questions? All right. So let's talk about breakthrough propulsion.
Can you ask if there's any online?
Are there what? Oh, are there any questions? Oh, hang on. I had the volume down. Are there any questions online? Okay.
Certainly before we end.
Oh, sure. Yeah. We can go as long as you want or until the library kicks us out. Okay. So this is not a formal membership, but there's a group of us that meet regularly, and it's called the ZC Institute. So that's actually a company, a private company. ZC stands for Zephyr and Cochrane. If you're a Trekkie, you know who that is, right? And so the guy that runs the company and founded it, Greg Hodgkin, is very much passionate about warp drive. And so he approached us because he was aware that we had done a review paper on warp drive some years ago. And here's the story of how that happened. I gave a talk like this to some freshmen and sophomores in a physics class, as I'm asked to do about once every year, every other year. And then as I try to make my escape back to my vehicle, a student, because they're faster than I am, tracked me down and said, I wanted to research with you on warp drive. And I just, all of the consequences of that flashed before my eyes. And I said, well, I don't do that kind of work. Maybe you could do a review article. And so he did. And the thing is, he did an excellent job. This is Joseph Agnew just wrote a really, really good paper. It was very well received at a conference. And then they did a press release, and that's how the word got out. And then that created the perception that we were doing that work, and it attracted a lot of very interesting people. We'll just leave it at that. So, as I anticipated it would, because that kind of thing happens. But that's okay. One of them was this guy, Greg, and he approached us and we showed him what we were doing with dielectrophoresis. And I said, I know a little bit about warp drive, but not a lot. And he said, well, here I've got this vast library. I collect papers and I'm always getting the new ones. And so that connection to him, that friendship, made it very easy and gave me no more excuses for trying to at least learn about it. And so I got a book on general relativity and realized how much I hate general relativity. So you look at this equation and just look at the man who came up with it. He's just there kind of making fun of us, It looks like a simple little thing on the left-hand side. All this is just the math behind the curvature of space. So space and time curve in this four-dimensional space, but this thing generates 16 partial differential equations. And I don't know the exact number, but I think there's hundreds of different multiple mixed partial derivatives that are part of what that giant matrix is. And then on the right-hand side, you've got some coefficients out here. This is SI units. And then you've got this thing called the mass energy tensor that says, okay, if you've got mass or dust or black holes or things that are spinning up and have weird energies, or if you have electromagnetic fields, they all can be devised to be put into this tensor to kind of tell you, okay, if this is your mass energy density spatial variation, this is how it's going to curve, and you solve those equations. But the problem for warp drive, so Alcubierre, I can't remember his first name, back in 1996 published a paper. Miguel, thank you. And when she came up with this space-time metric that says, okay, if we could curve space-time in which it expands on one side and contracts on the other, we could go faster than light. And the modern day perception that we could do FTL warp drive propulsion was born with that paper. And ever since then, people have worked on it to try to make improvements, because in the original paper, he needed the entire mass energy density of the universe to generate this field. And so it seemed like it just was not possible. And people have chipped away at it until they've made it smaller and smaller and smaller. But the problem is this term, 8 pi g over c to the fourth. G, that's the gravitational parameter, that's Newton's parameter, that guy, is like 6.67 times 10 to the minus 11. Then SI units, I can't remember all the units there. And then in the denominator, we have c to the fourth. C is a big number, 3 to the 8. And so 3 to the 8 times 4 is 32. So you've got minus 11 divided by 32 makes it the coupling between mass and space-time curvature just impractical. And so it's like, so the math is really, really hard. And the coupling between mass and space-time is just terrible. And so it's like, God, why do I even want to bother with this? But then I found out there is a subset to general relativity that is, now this looks harder because this is a lot more equations and it looks intimidating, but it's a lot like Maxwell's equations. So if you study Maxwell equations like I've had to for the version of fusion that we look at, this is not bad at all, believe it or not. So what this is saying, so this is one version. It's a subset of general relativity. It doesn't work for everything, but it does give you some intuition about where to look. This particular form of the equations was derived recently by L.L. Williams and Nathan Enon, some physicists that are kind of trying to take a fresh look at things. Some of you who follow warp drive or advanced propulsion probably heard of Ning Lee, who was a professor at UAH some 20 years ago. She did stuff like this, and before her, Bob Forward and Brzezinski and maybe how put off, I'm not sure about that one. But anyway, this paper cites a lot of the usual suspects that have done this kind of thing. So anyway, what this is saying, basically this EG term, this is the electric field. This is basically your standard gravity. This right here, this is the EG term, and it's generated by, this is the in mass density. So you can figure out how to convert this from that to a mass source creating gravity. So this is your standard thing. There's this other little term that shows up, 3v squared over 2c squared, where c is the speed of light. So if you can stir the pot, so to speak, and get close to the speed of light, you can kind of augment this a little bit, but nothing exciting just yet. And then there's this magnetic field-like term, which turns out, have you ever heard of frame dragging? I'm sure some of you are physicists and probably know already what that is, but frame dragging is basically like putting space-time in a blender. Okay, so the earth spins and it actually stirs up those field lines a little bit and creates a new effect to it. And it's equivalent to the magnetic field, and they're generated in a very, very similar way. It's sort of a relativistic effect, and it's created by mass current, but it's amplified by this coefficient, which is 4 pi times that stupidly small number divided by c squared. It's like, what can we do here, right? Okay, but if you expand it out and you consider this term up here expanded out in terms of its electrical properties, maybe we could do something, because c is not a constant. C is, as we've measured it, roughly 3 times 10 to the 8 in a vacuum, but in materials, it's very different, and you can slow it down a lot. So I think that's where one of the ways that we can improve on this, because you have the relative permittivity and relative permeability, both of which can be very, very high in certain types of materials. And now that we have this magic metamaterial thing, we might be able to really engineer some fantastic properties if we start looking. But in addition to that, if you start thinking about 2 mu g Jm, Jm is mass current. Well, where's all the mass in a particle? It's in the nucleus of the atom. So if you start thinking in terms of, well, gee, that's just kind of like stuff spinning around really, really fast. So if we could maybe orient all the nuclei in the same direction, that might give us a better coupling between our mass source and then these observed fields. So I don't know if that's going to lead to anything or not, but that's where I'm interested in looking to see where material properties could give us an augmentation. So I'm not the first person to think of these things at all, but this is kind of the thing that I'm interested in looking at. So we're looking at this. There's always these wild claims that come out about asymmetric capacitors. Some people, you have a camp of people say it's all ion wind, and some people say, no, there's this magic part. If you do it just right, you can still see a thrust and all that. And so we have the ability to test those sorts of things. And so we try to position the lab to be able to look at that stuff just to see, because it's not hard to test. We can argue one way or the other, but if we can actually test it, that's where the proof is. And so we look at those sorts of things. There's an idea that we're going to pursue this summer that I'm not going to telegraph, but if it's successful, I'll talk about it. That actually has nothing to do with this. So we're always on the lookout for ways of cheating the rocket equation. So we're always trying to do this. But in terms of where you want to go with fields, in my opinion, this is the place to really look, is to look at this and think in terms of how can you get these material properties to be augmented in order to slow the speed of light down, so that you can have terms like this to sort of augment and generate a more measurable gravitational field. So that's kind of my thinking on the topic right now. We've got a lot of people in the world working on this problem and different aspects of it. It's really hard sometimes to tease out what's legitimate versus what is frou-frou, if I can use that term. But it's all exciting, because it seems like, because of the way we can interact now with everybody using Zoom and being able to go online and talk and exchange ideas, that things seem to be accelerating. So I'm very optimistic that we're getting closer and closer to being able to do this. So with that, I'll just kind of wrap it up, and glad to take all the questions you want. So we're the Charger Advanced Power and Propulsion Laboratory. We're developing expertise in fusion, pulse power, and high voltage especially. And we're really excited about dielectrophoresis. It's kind of our new toy, which we think we can make an artificial gravity environment for crewed space flight. It's also good for debris remediation and material separation and recycling. And the main thing, the most important thing, is that we're here to train our students while developing fusion sources, high voltage applications, and advanced propulsion for the next generation. So with that, thank you very much, and I'm glad to take questions.
So Bert, can you hear me?
Yes, I can, Ronnie.
If you can open it up for questions from Zoom first, we have to end the Zoom call right at 7.
Yep, no questions have come in at this point. If anyone is online and would like to submit a question, please do right now. Nothing at this point.
But, my question is,
Yeah.
about fusion, you say superconductive magnets. There's material discovered on UA called YBCO. Has that seen any application in any fusion devices?
You're asking about the
Like barium copper oxide.
was that the superconductor that was discovered at UAH? Yeah. So I think that and derivatives of it had applications in breakthrough propulsion back in the 90s and early 2000s. At least I think it was similar, because I remember people like Tony Roberts working on that, because when I was a student and I got to work at NASA, I didn't do that work, but I got to be around it and see it and that kind of thing. In terms of fusion, it is now. And I don't know if they were using superconductors for either. I think they were, because basically you're limited to whatever the saturation magnetic field is for that material. And for either, it was like 2 or 4 Tesla. That's all they could get. And it's a huge field, by the way. But with these new magnets, you can get to 20 or 40 Tesla, and it shrinks the volume down a considerable amount. So I guess that's all I've got on that now. Basically, it was invented to do magnet fusion, magnet fusion energy, tokamaks and things like that.
Bert, do you have anyone else?
Nothing at this point.
We have time for a few more questions.
Dr. Cole, what happened to, the official, what happened to Nate Lee?
I have no idea.
She had somebody ran over and she had a auto accident.
So that's.
Disabled and she died.
Okay, I've
She
talked,
never left Huntsville. She worked for the Army.
okay, I know.
Started her own project, her own company, worked for the Army. And somebody ran her husband actually had a heart attack. He saw her get hit. She was disabled the rest of her life and died a few years ago. It's been buried. She's very local.
Well, I talked to Tommy about it a year and a half ago, and he's still doing papers on some of this, he basically, some of the phenomena and some of these superconductors. And he talked about this phenomenon that Nate Lee was doing. You talked about this, the medium specific.
Yeah.
And phenomena there. It was interesting. He had more mechanical issues of building large discs. I think they were going to go to a external methodology of spinning, creating these vortexes. Did you ever work with any of those concepts?
So I didn't get to work on it directly. I got to sort of dwell around them, so I got to see some demonstrations between him and then I remember another guy, Richard Eskridge, that worked over there. And he did some really exotic stuff in which they generated these massive electric field gratings that just exploded stuff everywhere. And then I remember he retired and formed a company, and I don't know what he did since then. I haven't really seen him in a long time, so I don't know.
Also, about 3 years ago, you made a big conference.
Oh, really? Oh, okay.
A little bit. It seemed like some really interesting, flight stuff they couldn't really talk about. They're genius guy.
Oh, yeah.
We did high voltage stuff on the product with Richard, and he would test our high voltage exciters.
Oh, so you do pulse power?
For detonation, we do a lot of that.
Oh, cool.
So we have a product. Richard helped test it. It's hard to get a true reading of the joules out,
Mhm.
not because of your load. So he
Yeah.
was doing that in NASA. So,
Mhm.
yeah, it's a small world.
Oh, yeah, it is, it is. Yeah.
Question in the back.
So you mentioned magnetic nozzles earlier. I guess could you elaborate more on the type of fuel tracks you were seeing, and are any tracks interesting effects from different curvature or varying curvature in the nozzle?
So that's actually something that we're doing as part of our NASA grant that we have now. That's a good question. So if I'll go back to one of the pictures on that. All right, so first off, if you go with, you want to have something in which it's directional so that there's a pressure associated with magnetic fields like V squared over 2 mu naught, or mu naught is permeability free space. So you want a pressure gradient to point out the nozzle so the plasma goes that way, right? And when you wind a solenoid, which has been kind of the canonical description of what a nozzle would probably look like, we tried with different simulations to do that, and people done 2D MHD and never could get anywhere with it. They published and they said, oh, we're making progress, but then they just kind of quit. And so I did what I always like really kick myself when I'm in the middle of doing these things. I'm glad I did it later. But there was a workshop where I said, we're going to have the first demonstrated simulation of a nozzle. And it was the night before, and I still didn't have one working. And I just kind of helped. And what was happening is the plasma runs into this solenoid field and it creates these weird instabilities and it just sort of catches the field. Or if you give it some motion, like give it a kick motion, just cheap, so send it out the nozzle to start with, it goes, it comes back and sticks to the field. You couldn't get it to separate from the field. So I said, well, let me just try this way. I'll just make and actually I was a little more thorough with the knees. I took it and just went out with the cone and then came back and then down with it like that. And so those axial windings, actually it just worked. The plasma just went straight out and I got a good specific impulse. And so that was kind of the birth of this new idea that we had, or so I thought. So one of the things that I do for fun is just get old electronics and take them apart. I just want to see what things are made of and what's in there. And one of my favorite things to take apart is an old CRT based television. People just throw them away, and I'll drive my wife crazy because I'll be like, oh, we gotta get this TV, it's beside the road, there's a flatback transformer in there I need, she's like, oh God, not again, and so we get it. But anyway, 1 minute, okay, so I took it home, take it apart, and there's a thing on it called a diverter yoke, which drives where the electron beam shines on the phosphor screen. And that diverter yoke, in which the technology was developed in the 1920s or 30s, has those axial windings. So they figured this out 100 years ago. I thought I was smart, but yeah, no, they figured it out already. I just caught up to 100-year-old technology, touching tomorrow with yesterday's technology today. That's our motto. But the windings are really super important, and it's not clear why some work and don't work yet. That's not worked out yet. It's open problem. Good question.
All right, thank you very much, Professor. Round of applause. So, Bert, I'll hand it to you for final comments, and then I have a few instructions for the audience, but I'll wait till you close the Zoom.
Well, thank you so much, Ronnie. Thank you, Jason. That was really a very fascinating discussion, and we appreciate you taking the time out of your busy schedule to present to our members. It's obviously an important aspect as we look towards space exploration. So thank you, and thank your students, and everybody who's joined us. Thank you for joining us this evening, both in person and virtually. So, Ronnie, I'll turn it back to you for any final comments.
You can go ahead and shut down. I'm going to be talking about post-meeting socials.
We're having a little trouble hearing on this end.
So we have half an hour to clear down and put things away and clear out. So we have to be out of this room at 7:30.
Yeah, Bert, you can end the Zoom.
Oh, okay, everybody.
I got it. I'll do it, yeah.
I'll be turning off the Zoom, everybody.
There's NSS.
Thanks, everybody.